Hi, so today we're going to be proving the Pythagorean Theorem, and as you know, it's one of the most important theorems in Euclidean Geometry. And well, I have already made a proof on it using a really simple proof, and today we're going to be taking a look at, well, the historical proof, right? The one that's found in Euclid's Elements book, which is the basis for Euclidean Geometry, and I think it was one of the first books which recompiled all of the mathematical, or almost all of the mathematical knowledge up to that time. So, of course, in most cases, we will need some previous results in order to prove this theorem. And we actually just need two results, which are already given in Euclid's Elements book. Well, Euclid's Elements book, it's divided into different books. In particular, Pythagoras' theorem is proven in the first book. I'm not too sure now which proposition was it, but I think it was proposition 47 or so. But well, we're going to be needing proposition 4 and 41, and just really quick. Proposition 4 just tells us about the congruency of triangles. That is, if I have one triangle here, T1, and another triangle here, T2, then they will be exactly the same. What Euclid mean by the same, he just meant that they have the equal area. Well, they will be the same if, for example, this side and this side are equal. That is, if A equals D and C equals F, and I'm just erase this, and also if alpha equals theta, then this is an if and only if area T1 will be equal to area T2. Okay, so this just really means that if they have the same sides, this side is equal to this one and this one equal to this one, and they share the same angle, then necessarily this other side will have to be equal to the other one. And if we have two triangles with equal sides and this equal angle and everything, well, these two angles will also be the same. This angle will be equal to this one and this one to this one. So really what we're saying is that, well, we might have these two triangles in space, maybe they're flipped or whatever, but they have the same area, and there will be some way of putting one on top of another so they're exactly the same. No gaps are left. I mean that you cannot see one when you put the other one on top of it. So well, this is really just a really basic theorem or proposition, okay? Well, this one might be a bit harder, at least from reading from Euclid's books, because at that time they did not use our notation. They just stated things by words and maybe made some pictures, but they didn't use things like variables. Well, they did call names the lines and angles, but they didn't express mathematical results with variables like, for example, this. So well, what this is saying is that if I have a base, okay, of some length that I'm calling base, and a height, another parallel line here, right, this is one segment and this is a parallel line, and it is separated by height, which let's just call it h, and this will be capital B. Then Euclid's proposition 41 just says that I can construct any parallelogram, right? It has to have sides parallel 2 by 2. With this base and this height, we'll have the same area as, well, sorry, we'll have twice the area as any triangle with the same base and same height. That is, if you know basic geometry, you'll know that for any triangle, its area is equal to its base times its height, right? In our case, base is equal to capital B and our height is equal to capital H. Sorry, this is wrong. Sorry, I was thinking of parallelogram over 2. So, area of the triangle. Now, the area of a parallelogram is really similar. It can be any parallelogram, okay? It's really similar, but in this case, area, let's just call this B, and this height, right? This distance, let's just call it H. Well, the area is just base times height, or B times H. Well, from this, it immediately follows that the area of the parallelogram is twice the area of the triangle. And this is exactly what's going on in this proposition. The thing is that how it is stated in Euclid's Elements, it's actually, from my opinion, it's really messy and hard to understand, but it's understandable because there was not this kind of notation or this notion. So there were these notions, but not the notation that we use today, which makes everything really easy to understand. So base and a parallel line which is separated by h, which are they have the same height. So I just partition it here. So we have a triangle with this base and this height, and a parallelogram with this base and the same height. So it will follow that the area of the parallelogram is twice the area of the triangle. So, well, let me just erase this and actually start with the proof. It's actually a really smart proof using these two propositions. So, what does Pythagoras' theorem or the Pythagorean theorem say? Well, it says that I have a right angle triangle, that is a triangle with an angle of 90 degrees. Then these two sides, which are the shortest sides, catetos in Spanish, I still don't know how to say it in English, haven't looked it up. Well, then this relation will follow, that a squared plus b squared equals to h squared. Again, in Euclid's book, it's not stated that way, it's stated in terms of areas, but with our notation, we know that a squared and b squared are just areas, and h squared too. So, well, let me just try this for a minute. What Euclid thought was, we just constructing a right angle triangle, and let me just do it here, and he constructed it this way. So then we will have our right angle here, and I will be using our more modern notation, okay? He will call these vertices and everything, but I will use more modern notation. So I'm going to call this A, this B, and this H. Now if I construct a square with side A here, it's really badly drawn, but you get the idea, I hope. Then let me just do it a bit more square. Okay, with side A, and this would be side B. Okay, and these are, hope that's clear, it's the same line. So, this area is given by a squared, and this area is given by b squared. Then, if I construct another one here, which will be bigger than both of them, then this area will be h squared, where this height is h. So what we want to show is that this area plus this area equals this area. How are we going to do it? Well, we're going to be using, as I said, these two propositions, and let me just erase this and see how we're going to do it. Well, first of all, we are going to draw a line here. How are we drawing this line? Well, we're just making it perpendicular to this base, right here, or perpendicular to the base, and just making it go here. And no, in fact, I will use some names for vertices. I'm going to call this A, this B, and this C. Okay? Now, as you see, I have separated this square into a rectangle and another rectangle. This height, or sorry, getting ahead of myself, this we'll call, how do we call it? Let's just call this E, and this we'll call it F. Just notice this triangle is H and E, and this one is F times H. So we have a base, H, and a parallel line here with height E. Why don't we construct some triangle, maybe try to use this proposition? But to do it, this is going to be my canvas or my base one, and I'm going to draw everything right here so it's clearer. Because I think it's going to get too messy if I do it just here. So, just using names, this is E. So, I'm doing the following. I'm just transferring all of this here. Well, before that, let me just say that I'm also going to draw this line. The line going from B to E. Why? Because we have a triangle right here. Okay? Let's just put it here so it's clearer. So we have this base, but this base, it has a length H, and we have a parallel line here, which is going from B to, what we'll call this, F, capital F. So we have a line going from B to F. And actually F should be just right here. what are we constructing? Well, we're constructing this rectangle right here with height E. So this will be height E, and so we are drawing this. But now we said that we are also going to draw this triangle. This triangle is going from just E, this is A, and it was going from EABE. EAB, okay, just join it here, and going again to E. So we are in proposition 41. If we call this triangle T1, and this parallelogram P1, this proposition tells us that if we split them, okay, try to do it in your head or draw it, the area of the parallelogram is twice the area of the triangle. So from this we get, and I'm going to put these results here, that area of P1 is equal to twice the area of T1, where I'm calling this T1, okay? And actually, I am going to be drawing it here, because I don't want you to get mixed up with next things. So this is F, this is E, this is E. Really, you could just have said, okay, just base times height. This parallelogram is H times C, and this one is H times C over 2, and you get that is area. But we'll try to do it Euclid's way, more or less. So, and this one. I should actually just use some color, right? So, and this one right here, and there we go. So this one was A, and this one was just B. Yeah, and we are calling this T1 and this P1. I hope that's clear, because I am going to erase this. So you have it just there. Now, in order for this to not get too crowded, I am going to erase this. But before, just notice the following: that this triangle, the EAB triangle, has, well, this height is H, this side is A, but notice that this angle right here, which I'm going to call alpha, is nothing but this angle right here plus 90 degrees. So what if I call this angle theta? Okay, just call it theta. Then from this we get that alpha is 90 degrees plus theta. Okay, it's just 90 degrees plus theta. So just have this into account. Okay, I have drawn it here, so I am going to quickly erase this triangle, because I don't want the picture to get too crowded. So let me just erase all of this. And now, okay, we have our first result. But we are going to do something that I think it's actually really smart. We're just going to flip it. That is, we're going to construct the following triangle. Just note that this is theta. Okay? So we're going to construct the triangle going from, what we call this, H to A to C. Okay? How we're constructing? Well, we're just doing this. But hey, what is this triangle? We have a triangle with this right angle, this theta, A and H. By proposition 4, same sides and same angle means they're equal, at least in area. So all we have done is taken the triangle that was right here and actually just flipped it around this axis, around this point, and put it into here. Oh, sorry. So I'm gonna put this result here, this one, for you to remember. So this was alpha, this was A, this was H, A, E, and B. And alpha is just 90 plus theta. Erasing this, we are ready to apply proposition 44 again. But how? Well, in this case, the base is A. But what is the parallel line? It's this one, right? It's the line going all the way here, from I to C. So instead of just looking at it here, I'm going to flip it and put it here. So our base is going from H to A, H and A, and what is its length? It's just A. Well, what is the parallel line? Well, the parallel line is this one, but it has a height of A, right? Because it's just a square. So our parallel line let me just put it here. Where does it stop? Well, sorry, it starts at H and it stops somewhere about here. I, and where our last point is the one going from A to C. So, what is our parallelogram? Well, it's just this one, right? A, 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 A. So, this is our parallelogram. And our triangle is just the one going from HA, CH. So, HA, CH. Let's call this T2 and let's call this P2. Right? Parallelogram 2 and triangle 2. Again, we have the same base, we have the same height. This relation will hold for areas. Okay? Sorry, this is should be yes. This relation will hold for areas. So again, we just have that the area of how did it? Okay. P2 is equal to twice the area of T2. Okay? So let me just put this result here. Area of P2 is equal to twice the area of T2. But just notice one thing. As we said, what is the angle right here for this triangle? For this triangle right here. And let me just draw it. Yeah, let me just draw it here. So, for this new triangle, really, let me just backwards. So, A, H, right? We're going A, H, and well, this side, we don't know the length. We could, but we need some things. Don't need it now. And H. So, sorry for my handwriting, it's awful today. Oh well. And C. So, what is this angle? Well, this angle is 90 degrees plus theta. Okay, so 90 degrees plus theta, but hey, wait a minute, as we said before, this is just alpha. So we have the same angle. Let me just call this phi so you don't get confused. Same angle, same length, A, and the other length is actually the same, H. So the area of this triangle and this one are the same. So the area of T2 is equal to the area of T1. What do we get from this? Well, it's just easy to see that the area of P1 is equal to the area of P2. This implies, if and only if, that the area of P1 is equal to the area of P2. But what is P1? What is P2? As I said, this was going to be P2, so let me just write it here, and this is going to be P1. So this area, right here, is exactly the same as this area, right here. Okay, so this is our first result. Let me just erase all of this and get to the next result. Okay, I hope this is clear, but here you have the summary of what we have achieved. You see, we only needed two properties, sorry, two propositions in order to prove Pythagoras' theorem. In the previous video, we actually just needed one, which was Thales' theorem, but well, here we are using two. So, and well, let me just erase this, and yes. So how do we actually keep going? So, okay, because we know that P2 and P1 have the same area, but what about B and this one? So how do we do it? How do we work this around? Well, we are going to use the same exact idea. We're going to notice that, hey, I have a base here, H, and a height, F, and I have a parallelogram, this one. We're going to make another triangle. So we're going to just do that. Let me just destroy for a bit, because my eraser is actually pretty bad. So, H. What do we call this? Let's just call it capital G, right? Okay, so we're going from G to C. And what is the height? Height is just little f, or lowercase f. So, F and capital F. Let me just do it like this. Well, let's construct our rectangle. And, well, our triangle is gonna look like this. Okay, it's gonna be the same, but we're going from B to G. Why? Because, well, it lies on the same parallel, it has the same height and the same base, so we can actually use our our proposition. So, just like this, okay. And just notice that, well, it has side H and side B. Okay? Let me just call this angle, what do we call it? Let me just call it gamma. Why not? It's gamma. From this we get that if we call this this first parallelogram P3, right? P3, and this triangle T3, why not? Well, then let me just use here. The area of P3 is twice the area of T3. When I write A, I just mean areas, okay? So again, we have that. And I am going to draw this triangle here because we will need it afterwards too. So, this triangle has base H and side B. So, H, B, and this angle, we're just going to call it gamma plus 90 degrees. Right, because it's just gamma plus 90 degrees. This, well, we don't actually care about, so GCB, well, this is just a B, C, B. This is our triangle, I hope you can see it well, and it's just this one, okay? So let me erase this again. And we are just one step away from proving the theorem. How are we going to do it? Well, first of all, we're going to erase this, because it's getting messy. Yeah. In many sites or many, I don't know, in books or everything, wherever you look for proof like this, sometimes things get too crowded, right? They start drawing lines and then another line, another line, and actually my head gets so, I don't know what's happening anymore. So I prefer to go erasing it or go step by step and then just keeping the results here. So now, what are we going to do? Well, before we draw one that was between this square, so let's see if we can find another one. And, well, if I take this base, let me just call this B, and I take this one and go here, we're calling this, let me just call it capital J, I'm running out of letters. So we have that new triangle. There we go. Again, height, well, this is the same now, okay? I think it's a bit twisted, but this is actually just one line, okay? So, what is the height? The height is B and the base is B, so we're going from B and just call this C and J. Well, going here, call this K and we get K. So, constructing again this height, well, the height was again B, so, sorry, too big maybe. Well, what is a parallelogram? It's just B, 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 it's like B, C, G, K, so B should be around here. What's the next step? Actually, practically the last step of the proof. Just make this triangle right here. It was, oh yeah, sorry, this is getting mixed with the previous picture, so let me just, okay, so this is actually A, okay? So we have, this side is H, B, and well, as we know, if we call this T4 and this P4, we see that, hey, again, the area of P4 is twice the area of T4. You can either do it by base times height, kind of area, or you can do it by proposition 41, which is exactly the same but formulated in a more weird and not weird but harder way, I think, to see. and visualize. So, so this is the thing. We call this P4 and this P3. We are almost there, but we need again to see that, well, let me just get this triangle straight here. So calling this triangle T3, sorry, T4, right? So it was AJC. So AJC. And this is H, and this one is B. What is this angle? Okay, we need this angle. Well, it is gamma plus 90 degrees. So, hey, this is gamma plus 90 degrees. But wait a minute, this is the exact same angle there. So let me just call this alpha, and this is also alpha. And they share the same sides, right? HB and the angle alpha, and HB and the angle alpha. So by proposition 4, again, this triangle and this triangle are the same, which means in Euclidean literature or Euclidean language that two triangles are the same, I mean, if they have the same area, in our terms. So, so area T4 is equal to area T3. Erasing this to make more space. Let me just rub it out. Using this, so we get that this, even only if really, a P3 is equal to a P4. Right? So, what do we have so far? Well, we have quite a messy picture, so I am going to erase all of this and try to make it a bit cleaner, right? Because things are getting too messy now. Okay, so of course now we are also going to make an assumption, but well, it's not more than an assumption. It's again, I think, another postulate that we can actually add areas. That is, to have two squares side by side. The area of the rectangle which will compose it is, well, the sum of the area of the squares. But you see what I mean in a minute. So let's just do this really big. So we have a right angle triangle, and we have chosen the right angle to be here, and I don't remember exactly what names I gave everything, so I'm just going to call this A, B, C, and I hope that's right. This was H, this is A, and this is B. Our right angle triangle, we just flip it. Making this square, it looks more of a rectangle, it's a square. So H, another square. Not too much of a square, but well. A, okay, first square, second one, well, we call this P2, I think. And let's call the whole square, so, everything, let's just call it PH, okay, the whole of this square, and we will later on split it. And our last one is just this. So we call this P4, I think, right? 4. So again, we will use our magic line, which let us solve everything. That is it. Not too straight, but well. So what we have done really here is just splitting this big square into two smaller rectangles. So we have this rectangle plus this rectangle. Intuitively, you'll say, okay, the area of all of this is the same as this one plus this one. So that's what we're going to be assuming. When I'm saying that, well, if we call this P1 and P2, we're going to say that, well, the area of P1 plus the area of P2 is the same as the area of PH. This just means that this area is equal to the whole area. So from this equation, we see that, wait a minute, the area of P1, sorry, this is not P2, it's just P3. What am I saying? Okay, so this is P. Oh no, okay, yeah, this. I'm getting mixed up. This was P2. Sorry. So we're saying that AP1 and AP2 equals to APH. But from this we get that AP1 is equal to AP. This is P3. This is P3, sorry. Yeah, I knew that I was getting something mixed up. This is 3. Now, the area of P1 plus the area of P3 is equal to the area of PH. Now, the area of P1 is equal to the area of P2. That is, this one and this one are the same. All of this is the same as all of this. So, we say that AP1 really substituted by AP2. And we're adding AP3. But AP3, which is this area, is the same as AP4, which is all this area. So AP3 equals to AP4, meaning that this is AP4, and this is still equal to PH. This is already a Pythagorean theorem, but I'm just going to put it here a bit cleaner. So what we're saying is we have gone from this area plus this area equals this area to this area equals this area, and this area equals this area. So this plus this equals all of this. Okay? I think that's it. So it's really interesting, right? If you put liquids here, really it has to be really thin liquid, because otherwise you'd be talking about volumes. Or what? If you put a really thin layer of liquid here, and you literally drop it here, if this is full, this will also be full. And likewise, if this was full and it dropped, the liquid would drop here, it will also be full. So there is actually some quite cool visualizations of the Pythagorean theorem on YouTube. So I urge you to look it up. Well, just going on to what we have, we just need to say that, well, P2, the area of P2, so we know the area of a square is a squared. Well, side by side. This is another postulate, you could say, because it's such a basic result that I don't think you can derive it from anything, or if you can, I'm not too sure now. So, well, you could derive it from the unit square, but this would be a postulate, but well. And this one, AP4, well, this is just side by side again, so this is just B squared. Then, from this equation, we get that AP2 is just A squared, plus AP4, the area of P4 is just P squared, and this is equal to H squared, right? Because APH is the area of all of this, which is this times this, H squared. So, and we have proven the theorem Euclid's elements way. So, well, yeah, that's it for today. I hope you liked the video, and well, see you in the next one.